Okay, here's another example of a complex circuit. I'm juggling around the type of information that I'm giving to you. Okay, so here we go. I've got a 6-volt battery and I've got 4 resistors. A, 75 ohm. B, we don't actually know. C is 20 ohm. And D is 30 ohm. Okay, so let's fill in things that we do know. That's a great way to get started. Resistor D is 30 ohms. Resistor C is 20 ohms. Resistor A is 75 ohms. I do not know resistor B, and that's about it on resistances. 6 volts, and then resistor B has a potential difference of 1.5 volts. Okay, so there are a couple ways that we can go about this. I'm going to start this kind of the more straightforward way, which is a little more comfortable for you all. And here we go. Let's see. I can't really do anything with my resistance column because I don't have enough to start playing around with equivalent resistance, at least not the way that we're familiar with. More on that in a minute. I have no information about my currents, so I can't use junction rule. And I didn't explicitly say it, but we can't really solve anything with Ohm's law because we don't have enough information in any given row, which means let's go to loop rule. Okay, so I go across the battery. I start here. So that gives me plus 6 volts. That raises me up to a height of 6. I go across resistor A minus delta VA, which I don't know, but that's okay. I'm going to keep going. I'm going to go over here towards resistor B because I know the potential across resistor B is 1.5 volts. And then I keep going over here, and that brings me back to where I started. That's a closed loop, so we end up with 0 as a result. Now, real quick, I want to point something out. On this branch, we have a drop of 1.5. On this branch, the total branch, we must therefore have a drop of 1.5 as well, because they meet at this height, and then they meet again at that other height, which means if this one drops down a height of 1.5, the total height drop of this one has to be the same, 1.5. Now, that's one thing, especially as you're starting to work through with some of the questions on the AP exam, it helps to keep track of that one branch, the total potential drop, has to be the same for another branch. That does not mean that the 20 ohm has a drop of 1.5. It means that the drop on C and D together add up to 1.5. Right now, that's not going to help me to do very much, but we're going to come back to that in just a moment. We're going to see how this ends up that way, why you can draw that conclusion. On the AP exam, they may only give you this part of the circuit. They may not tell you what's going on with the rest of the stuff, so you may not be able to do what we just did here. We do find out that delta VA must be equal to 4.5 volts by loop rule. And because this is 4.5 volts, that means that go up 6, come down 4.5, and then these two together must drop us down 1.5. It's the same thing that I mentioned before. The potential drop on one side of the branch must be equal to the potential drop across the entire other branch. They all have to have the same. Now, real quick, I'm going to take us off on that tangent and find out something where this could be, if we didn't know what was going on with this, because that matches some more of the AP things, I'm going to give you a more challenging approach of a way of looking at this. Well, I don't know what the potential drop across C is, and I don't know what the potential drop across D is, but I do know that since those two are in series, I could replace them with an equivalent resistance, REQ, of, well, they're in series, so 20 plus 30, that would be 50 ohms. Great. And I know that they have a potential drop across them, total, the two of them together, which is what the REQ represents, of 1.5 volts. So I could find, by applying Ohm's law on my invisible equivalent resistor, I'd have 1.5 volts divided by 50 ohms. I would find that the current going through this equivalent resistor is 0.03 amp. That means that we would have 0.03 amp coming in, 0.03, and we would have 0.03 amp coming out. And if we then take that back, so it's 0.03 coming out, 0.03 coming in, that's how currents work. That means that in real life, these two together into the green, we must also still have 0.03 coming in and 0.03 coming out, which means it must go through C, 0.03, and D, 0.03. Well, let's see what they come up with. So 0.03 times 20, that gives me, oops, I'm about to write it in red, I need it in blue, 0.6 volts, and this one, 0.03 times 30 is 0.9 volts. And when we add these two together, we find they do come up to 1.5. If I were to go the other branch, I'd have plus 6 minus 4.5, so that's 1.5, minus 0.6, so that would be 0.9, and minus 0.9, we end up back at 0. So here's an advanced way that you can start applying equivalent resistance even if you're not filling directly in other resistances in the table. Now, I'm not necessarily recommending you do this in class. I will usually give you these. However, on the AP exam, being able to think about applying these things in a more advanced way can be very, very useful. Okay, great. Let's pretend that we didn't do that initially, and let's go through. We now know that we've got 4.5 volts here, so 4.5 volts, let's see, divided by, well, actually, I think we did need to do that in order to solve this completely. I gotta be careful with how I set this up. 0.06 amps is our total current. Now, with the stuff that I did here, I apologize. I think I did not give enough information on B for you to solve it any other way than doing this advanced approach. But this is good because a lot of times on the AP exam, they'll give you part of a circuit that you have to do an analysis on. So this is a good way of a little bit of a heads up on some of the advanced stuff that you'll need to do. Well, we've got 0.06 going in here to this junction, and we know that 0.03 is going this way, which means by junction rule, 0.03 has to be going the other way. And when I multiply this across, 1.5 times 0.03, I end up with, not multiply that across, delta V equals IR. Never get in too much of a hurry. I was about to make a mistake. Delta V equals IR. So if I want my resistance will be delta V divided by I, dividing both sides by our current. So I would need 1.5 divided by 0.03, and then I get 50 ohms, which we also could have predicted when we realized that the current split evenly both ways. The total resistance on this side is 50, and for the current to split evenly, the total resistance on this side must also be 50. Great, we're pretty much done. We also know that if the current going through A is 0.06, it's all coming from the battery. So that's my total there. And I take 6 divided by 0.06. My total resistance, we predict it to be 100 ohms based on Ohm's law up here. Let's see if that works out with our equivalent resistance. We know that this one becomes an equivalent resistance of 50. So I would have 50 in parallel with 50. So that would be 1 over 50 plus 1 over 50. So 1 over 50 plus 1 over 50 equals 2 over 50 ohms, which means that we end up with a total equivalent resistance of 25 ohms, 50 ohms divided by 2. And then we'd have 75 plus 25 would give us 100 ohms. That does end up working out. Now we could go through and we could find the power for each of these. Let's go ahead and do that as a nice example. So I would take 6 times 0.06. I end up with a power of 0.36 watts. On this one, I'd have 0.06 times 4.5. This one is 0.27. And then back over here, I've got 0.03 times 1.5, 0.045. We're getting to some pretty low power values here, wattage, if you will, times 0.6. 0.018, and then finally 0.03 times 0.09. 0.9. Great. 0.027. Great. And you could go through. We should see that all of that works out. Let me double check here. 0.36. Yeah. So they should add up to also verifying that energy is conserved. I'm not going to do that. You're welcome to double check. Because, the main thing that I want you to take away from this is being able to work with this in kind of a different way. Now, I'm not going to ask you too many of these in class, but you might see things that have smaller sections of a circuit in multiple choice questions, not large workout problems like this. So being able to work with your equivalent resistance and apply the potentials across them to find your currents might be very useful. This is also why, and I can't stress this enough, you have to have a feel for what each of the things do. Delta V's change over each component. Your currents, however, are not used up, not raised, not lowered. They continue and they stay the same. Each of these have different ways that they interact with components. Your delta V's will change, your currents will stay the same as they go across one of the components. Charge is conserved, and because energy is conserved, we have each of these reducing the height so that we can release energy from it.